Okay, good afternoon, ladies and gentlemen, and welcome to your colloquium, SERI Institute colloquium series. So today we have a special configuration in this room because we are hosting a workshop on the life on Titan. So we have several scientists here coming from everywhere in the US who decided together to discuss the potential of life on Titan. And at the same time, we also have Jason Barnes, who's going to give us a talk, a 1-hour talk. So Jason is the planetary scientist here. We have a lot of Jason Barnes in the US. There is a football, soccer player, basketball player, geophysicist. We have today Jason Barnes, the planetary scientist. Jason studies the physics of planets and planetary system, and his research involves both observational and theoretical studies of planetary geology and planetary physics. Jason uses NASA spacecraft to study planets in orbit around other stars, exoplanets, and the composition and the nature of Titans, the moon of Saturn. Jason got his bachelor at Caltech University in 1998, his PhD at University of Arizona in Tucson in 2004. Then he came in the beautiful California and stayed for a while here at NASA Ames for a postdoc, and then became an assistant professor of physics at the University of Idaho in August 2008. So Jason has a very long list of publications. I'm not going to talk about all of them here. 50 of them are related to the study of Titan and exoplanet, as I say. And today we'll give us a talk on the prospect of life in Titan's seas. In his talk, he will include a description of these seas, their chemistry, and hydrology. He will discuss new data and results, such as Cassini RADAR evidence of compositional variations between the seas and the detection of the first sea surface waves outside of Earth with VIMS, an instrument on Cassini. This is a remarkable research, and I hope this talk will give us a vivid proof that we indeed live in the golden age of planetary explorations. Please join me in welcoming Jason Barnes.
So I was a postdoc, as Frank mentioned, over at NASA Ames Research Center for a year and a half before I got my professorship. And while I was there, of course, you can't, as a scientist that's not actually a civil servant in Ames, you can't write proposals through Ames. So actually, my first funded proposal routed through SETI. I proposed as a member of the SETI Institute before I got my job, and then I took the money elsewhere. So I appreciate SETI's support. And the support they give for all researchers that are, especially postdocs, young people in the same vein. So today, I want to talk about what I study, Saturn's moon Titan, and to relate it to what SETI does well, especially the Carl Sagan Center for the Study of Life in the Universe, looking for life in other places and life maybe not as we know it, right? So this is a reference to what it seems like. So this is a reference to the old Star Trek series where Spock would have said, "It's life, Jim, but not as we know it." And the dearly departed Leonard Nimoy never said that. But it seems like he should have said that. So we all think he said that because it seems like exactly the kind of thing he would have said. So what do I mean by life not as we know it? Well, as far as what we need, the ingredients for life, we think you need three things. You need some sort of solvent. So some sort of liquid for molecules to interact in. You need building blocks, and you need an energy source. You need those three things, okay? And for the longest time, it's been understood that the word solvent means water, and the word building block means carbon atoms and carbon molecules, and the word energy meant sunlight. And so when we look for planets around other stars that may be habitable, we've assumed what we're looking for is somewhere that has liquid water, that has carbon, and that has enough sunlight to be at about the right temperature for the liquid to be, for the water to be in the liquid form. However, in studies of the Earth over the last tens of years, funded by at least to some degree, and driven by the astrobiological concerns, we've found that life on Earth actually can live in a whole bunch of areas that we didn't expect. For instance, that third element, energy, does not always mean sunlight. In fact, there are life forms, single-celled organisms that live off of deep sea vents, that live on disequilibrium chemistry coming out of the hydrothermal hot springs at the bottom of the ocean. There's even single-celled organisms, bacteria and archaea, that live inside solid rock, whose ultimate energy source is actually radioactive decay of uranium in the rock. And they're not a super diverse amount of life, but at the same time, this is a kind of life form you might expect to see anywhere on any silicate body. As long as there's water, you have this sort of radioactive decay, you might have the elements you need. So life not as we know it, according to Mr. Spock, may have been, some sort of energy beings that, took over the ship and everyone got to, act or something in that episode. What I'm talking about instead is altering the first of those three elements, which we thought was liquid water. You need liquid water in order for carbon atoms to interact in. If you look around the solar system, there's plenty of places that could happen, okay? That could happen on Mars, either under the surface or maybe under transient conditions, certainly possibly in the past. It could happen on Jupiter's moon Europa. Under the icy crust of Europa, we think there's a liquid water ocean. And you may have some mechanism of getting carbon down there. That might be a place we might look for life. Saturn's small moon Enceladus is similar in that we think there's liquid water underneath, and that water is spewing out into space. The other place is Titan, and Titan is different. We do think there's water on Titan, maybe 130 kilometer thick ice crust, and there's a liquid water ocean here too. But it's hard to get that liquid water to interact with all this carbon stuff that we see on the surface that I'm going to talk about in a bit. However, on the surface of Titan, there are lakes. In fact, this is a picture of Titan taken from the Cassini spacecraft. And what you're looking at here is these dark, patchy regions here are seas on the surface of Titan. So we've actually found seas and lakes on other planets than Earth. Okay? But remember, Titan is a moon of Saturn. It's 10 times further from the sun than the Earth. So there is ice that you're looking at here, and it's the rock. Okay? Ice is a rock on Titan. However, methane, which is natural gas, this is the stuff they frack for in Pennsylvania that you turn on your burner if you have a gas burner. Methane on Titan is sort of near its triple point. So methane on Titan can be a liquid, it can be a gas, it can be a solid. And in fact, we see all those. This is the liquid form that you're seeing on the surface of Titan itself. So these are liquids, liquid expanses of liquid methane and perhaps other hydrocarbons as well, ethane, maybe some propane, on the surface of Titan. So this sort of gives us a chance to test the first requirement for life, okay? Do you really need water? Are there other solvents that could work? And, if you asked me this 20 years ago, I'd have said, well, I'd been in high school, but I'd have said, how could you possibly, we're not even ready to go there yet, okay? We just have to establish where life could maybe work with water, and we can move on to that other stuff when we can even understand what we're talking about with water. But the fact that we've now found a possible place to test this in our own solar system, someplace we could actually visit if we had the money and the will, makes it a really compelling, I think, idea, a reason to start thinking about, can you have life form in a solvent other than liquid water? So that's what I'm going to try to talk about today is life in another solvent really viable? I'm going to focus on what we really have been doing. We haven't been able to look for life in these things because we haven't been able to get down to them yet. I'm going to talk about the observations we've done from the Cassini spacecraft that are going to help us constrain whether maybe this process might work, how it might work, and how we might go about exploring Titan in the future. So Titan, for those of you who aren't as familiar, as a moon of Saturn, it's the second largest moon in the solar system. It's much larger in radius than our own moon, but its mass is maybe about the same because it's made up a lot of water. The entire outer portion of Titan is made of water. But Titan is particularly interesting, and the reason it can support these lakes and seas on its surface where Mars can't is because Titan has a very high surface pressure. It has an atmosphere. It's the only moon with an atmosphere, and its atmosphere is actually has higher pressure than the atmosphere in this room. It's about 1.5 bars. So in addition, its composition is almost the same as Earth's atmosphere. Nitrogen. To first order, it's mostly nitrogen. Okay. We know there's no oxygen on Titan, and that's a good thing because there is all this methane in the atmosphere, and oxygen and methane, when they get together, they can have an explosive reaction. So we don't want that. There's no oxygen around, but there is this methane, and there's a lot of it too. surface. That's not going to work. Okay. Taking a look at how we discovered these seas, we actually did not know about these seas when we first got to Titan. Cassini, the spacecraft I work with, first arrived in the Saturn system in 2004. And at that time, there were predictions that maybe there was, Carl Sagan, in fact, that predicted that you might have seen a global ocean of liquid methane or ethane on Titan. But as you can see, when you look at Titan, there's no global ocean. I mean, an ocean would kind of look all the same everywhere. Instead, there's a lot of variegation and a very diverse surface on Titan. So clearly, there's no global ocean. But these lakes and seas that you see up here are actually right next to the North Pole. The North Pole of Titan's about right there. Okay? And like Earth, Titan has seasons. In fact, it's tilted about 26 degrees with respect to its orbit. Earth is tilted 23 degrees. So the seasons are about the same intensity. And like Earth, if you live on the North Slope of Alaska or something, or you try to winter over in Antarctica, the sun does not come up for months at a time, for that whole winter season. Well, when we arrived at Titan, it was the North Polar winter. And because Saturn takes 28 years to go around the sun, that winter lasts 7 years. So we happened to arrive right in the middle of winter, and the sun didn't come up on these lakes until much later after we got there. So when we first discovered Titan's lakes and seas, it was through the radar instrument. So the radar instrument on Cassini was designed to be able to see through Titan's atmosphere, which is kind of hard to see through in the optical. There's too much haze, too much smog, essentially. And so if you try to look through at longer wavelength like a radar, you can see right through the haze. And this is an image, a composite image actually taken of many radar passes of what the North Pole of Titan looks like. And this is how we first identified the lakes. It turns out these lakes are super flat. And the way the radar works is as it's flying by, it's sending out pings to the side, and that's how the radar works. So if you have a rough surface, that rough surface returns a lot of energy to you, and that's how you see, so bright things you see are rough. So here's this area right here on Titan is very rough. That's a mountain range. However, if you have a very flat surface, you're firing your radar beam to the side, you fire your radar beam, and like a mirror, that flat lake is going to reflect all the energy right away. And you're not going to see any of it coming back to the instrument. And so those lakes look very dark to radar, and that's what we see. So we have first identified these lakes as being areas that were totally black, almost, to radar. So that meant they were super flat. And it's hard to imagine how you can get something. This one is called Ligeia Mare. It's about 250 kilometers across. It's hard to imagine how you could have something 250 kilometers across that's flat to within a couple millimeters without having it be liquid. But that was the first evidence we had for what we were looking at. Here's a zoom in of what Ligeia Mare looks like in detail. You can see there are these sort of channels. These are in fact canyons of liquid, not water. I made a mistake that we're not supposed to make. On Titan, we do think there's rain. We see, in fact, clouds. We see thunderstorms. We see rain. And we see these channels. These channels are showing us that at some point on Titan, it does rain. That rain covers the entire surface. And that rain runs off through a channel system down into, in this case, this giant sea, Ligeia Mare, very similar to what we see on Earth. We do see channels on Mars that we think are probably not coming from rainfall. Those are probably coming from massive outflow from the subsurface at some point in the past. But on Titan, we see these channels in what are called a dendritic network. So a network that looks like the networks you see on Earth if you're looking at Earth from orbit. So it rains all over Titan. The rain is liquid methane, of course. So you're not probably going to have plants growing it. We're not quite at that level yet. But you have a broad liquids that occur seemingly almost at all latitudes or all places on Titan. This is actually a relatively new result just from last year, 2 years ago, I guess now, where we have these giant seas. How deep are they? How big are they? They're 250 kilometers across. Are we looking at a meter deep ocean that you could wade across? Or how deep is this stuff? And this is a very exciting actually result from the Cassini radar instrument. In addition to flying and looking sideways to be able to take images, the radar instrument can look straight down. And we did this to try to figure out what the topography was. If you're trying to figure out how tall the mountains are on Titan, you'd do this. And when you have an altimetry track, we send a radar ping down, and we wait for how long it takes for that ping to come back. So this is a plot of actually time, and time is inverted. This is how planetary scientists do things. So short time for the radar to come back is at the top, and long time is at the bottom, such that if you had a mountain, it would show up as actually looking like a mountain in this plot. And this is a function of distance along this track. And what you see is a very strong return from the very flat surface of the lake that we might have expected. What you also see is this return from the bottom of the lake that comes a microsecond later. And if you calculate how long it takes light or radio waves to propagate down to the bottom of the sea and back, you find that this sea, Ligeia Mare, is about 160 meters deep. So that's about, what, 500 feet or something? So this is actually not just some shallow lake like the Salton Sea down southeast of here, okay? This is a very deep sea, more maybe akin to Lake Tahoe or something in terms of its depth than something that's very shallow. And in fact, you can use this information then to calculate how much stuff, how much hydrocarbon is there on Titan. The answer is about 250 times more than the proven oil reserves on the Earth. So we tell Exxon they'll build a Keystone Pipeline XXL right to Titan. They'll suck it all down. We'll be in great shape. Maybe that's how we could get our project funded. Okay, so what is that stuff exactly composed of? It's actually kind of difficult to tell, looking from orbit at a liquid, what that liquid is made out of. One way we can do that is with one of the instruments I work with, which is the visual and infrared mapping spectrometer. So try to take its spectrum. It turns out this is pretty hard, and the reason is that because methane is near its triple point on Titan, there's a lot of it in the atmosphere. In fact, 5% of the atmosphere is methane at any given time. So this is kind of similar to water vapor on Earth, okay? So, you can get up to 5% water vapor on Earth if you're like in the tropics or in Puerto Rico or something, and you go out, you step out of the airplane. This doesn't happen in California because it's nice and dry. But you step out into a big tropical atmosphere, there's a lot of water vapor in the air. So similar to that, there's a lot of methane in the air on Titan. And that methane absorbs, actually, such that we take a spectrum. Here's a spectrum in the infrared. So this is wavelength of light on the x-axis. And you all are viewing this presentation out here at half a micron wavelength. So these are all wavelengths longer than the human eye can see. But using these, we can see down to the surface of Titan, but only at certain wavelengths. Because it turns out in these black areas, methane absorbs all that light. And so Titan just looks nearly black at these wavelengths. But there are some wavelengths which we call the windows, spectral windows, that we can see through. We can see the surface of Titan through these particular windows and down to the surface at that wavelength. And we're able to see one absorption line through one of these windows that's consistent with ethane. So methane is CH4, and ethane is C2H6. It's a little bit more complex hydrocarbon. So we think that there's not just methane. These things aren't pure methane. There's other stuff in them. And that's when things start to get exciting, okay? If you want to have life, you're going to need to have other higher order carbon compounds that are in these liquids along with the methane. And this is sort of our first indication that this stuff isn't actually pure methane, that this stuff may be more interesting. You can calculate from theory that the nitrogen in the atmosphere should also dissolve in these lakes. We also expect for higher order hydrocarbons to be there too, maybe propane or even more complex things that we've actually been able to see in the atmosphere so far, may be working their way ultimately into the lakes and seas themselves. And what this means is that, when you're on Earth and you're in a high, say you're hiking in the Sierras, okay, you come up, you hike up some huge cliff trail, and you're exhausted. You come to this beautiful alpine lake. You can be fairly certain that's made of water, okay? Titan is not so simple. It turns out on Titan, the lakes and seas may not all be the same because they have these different amounts of other substances that are dissolved with the methane. We think that Titan's lakes and seas actually might be quite different. And this is sort of somewhat analogous to the role that salt plays in Earth's oceans. So it turns out the Mediterranean Sea is sort of at a relatively arid latitude next to the Sahara there. And so there's a lot of evaporation out of the Mediterranean. In fact, there's so much that there's a net inflow from the Atlantic into the Mediterranean. What that ultimately means is that because there's more evaporation in the Mediterranean and there's a small inlet from which it's getting material, there's actually the salinity, the salt content of the Mediterranean Sea is higher than that of the general ocean. Similarly, If you go further east through the Straits of Bosporus next to Istanbul there into the Black Sea is fed primarily by a bunch of rainfall driven rivers from central Russia and Central Asia. And so that actually has a huge inflow of fresh water without salt. And the Black Sea is actually less saline than the ocean, even though it does interact with the Mediterranean, which is more saline, okay? So we think we're seeing a similar situation on Titan, in that if you have a lot of rain near the North Pole, the rain on Titan is mostly pure methane, because that's the most volatile stuff. That's the easiest stuff to evaporate. And so if you get rain of pure methane near the poles here, of course, near the equator it's warmer, and you get more evaporation maybe near the southern end. And it turns out all of these seas are connected via these complicated series of straits, such that if you rain here, ultimately that's going to wash things through Ligeia, wash Ligeia clean, and such that it might be nearly pure methane, whereas any solutes, anything that's dissolved in that methane, be it ethane, be it propane, or more exciting things, is ultimately going to be washed to the southern end of Kraken Mare, where there's more evaporation. So this is sort of like the Mediterranean down here, more dissolved stuff. This is sort of like the Black Sea up here, less dissolved stuff. So this is a prediction that we think may be being borne out by the fact that we can't see, the radar instrument has trouble seeing through the big sea here, Kraken Mare, and it can see through Ligeia easier, and that's exactly what you'd expect if there were more stuff dissolved in the liquid here than there is up in these other seas. So it took a few years. We saw these seas with the radar instrument in 2006, but finally, by the time we got to 2008, it was solstice. It was the northern spring solstice on Titan. And so the sun comes up in the northern hemisphere, and we absolutely start to see these seas. This is actually the very southern end of this big sea here, Kraken Mare, observed in the infrared. So this is still longer wavelength than your eyes would see, but not that much longer. You could get special goggles and view Titan and have it look like this. It turns out what we're looking at here is all this brown stuff near the equator are sand dunes, which we did not expect to find on Titan. That was exciting. The greenish stuff is the normal surface, presumably mostly water ice. And then you're seeing this dark stuff near the poles, which are these lakes and seas that we've just found. Shortly after the sun came up in 2008, this is a totally serendipitous discovery. We happened to be looking back at Titan. Normally I'm interested in the pictures where we're taking pictures from the front of Titan, the lit side, the sunlit side of Titan, where you can actually see what's going on the surface. If you instead look from the backside, mostly what you just see is a crescent with a bunch of scattering off of the haze particles in the atmosphere. Boring, so I wasn't looking at this image. But my colleague, Katrine Stefan, did look at this image. And what she found was when you look back at Titan, in this particular case, you see this huge bright spot on Titan. This spot is a specular reflection, or a sun glint, right? This is if you're standing next to a lake on the Earth and the sun's coming right in front of you, it's really hard to look down at the lake because it's super bright, because you get this reflection of the sun off of the lake itself. And this is what we've started to see on Titan, even at infrared wavelengths, not too far longer than the wavelengths we can see. The sun is shining down, and by looking at this giant specular reflection, this isn't really accurate. If I dialed this to the correct brightness, you guys would be like, oh my gosh, oh, don't hurt my eyes. Put your sunglasses on, watch this, and you can see these giant specular reflections. And we've actually been using these to try to learn more about what's going on, what are the physical and chemical processes going on Titan and inside Titan seas. So this is a more recent image that I was analyzing of one of these specular reflections on Titan. So this is an infrared image, so the fact that it's all beautifully blue, don't let that fool you. The blue color is actually 2 microns, which is about 4 times longer than the wavelength the human eye can see. But it looks blue for the same reason that Earth's atmosphere looks blue, which is that short wavelengths scatter more easily, and that's true on Titan as well as it is on Earth. So the atmosphere here looks blue, and you're seeing this bright pink glare. Oh, put your sunglasses back on. Okay. This is this giant glare coming off of the third of Titan's large seas. This one is actually a small lake called Kivulakis next to Punga Mare, which is another large sea. So by using this, actually, it's a great test for what Titan's atmosphere is doing. in order to measure sort of what the absorption is through all of Titan's atmosphere, it's actually really pretty hard. Normally, when we look at the surface, what we're seeing is light that's coming in from the sun, and it scatters and does something in the atmosphere. Then it hits the surface, which does something totally different. Then it comes back out through the atmosphere, okay? So when you see it, you don't know what you're looking at. What part is surface and what part is atmosphere? So I used to joke, oh, we need to send a mission to Titan to put a 10-kilometer by 10-kilometer piece of paper on the surface. So we know exactly what the surface is. It's white. And then we can pull out what the atmosphere is, okay? It turns out this is even better. It turns out the lakes are a perfect mirror on the surface of Titan. And this mirror allows us to essentially look at an entire transmission spectrum of what Titan's atmosphere looks like just by using the sun as our source. And it goes all the way down, it hits off the lake, and comes all the way out. In addition to using this for that, you can see that if you look very carefully, there's these little sort of pink spots right above the bright pink spot. So I'm going to talk about what is going on there. If you map where those pink spots are to a globe of Titan, so here's the north pole of Titan right in the center here. Here's this little lake Kivulakis that's the primary source of the specular reflection on this particular flyby. And this is Pungamare, the smallest of the three seas. And you can see that these bright spots are coming from the middle of the sea. Well, that's weird. What's going on is the sea itself looks kind of bright. That's the same way. This is a picture I took when you travel a lot. And now they let you use iPhones on the plane. You can really get some good pictures you can use for science. So if you look out the side of the window, normally if you're looking down on a lake, it looks dark. But if you look at a lake at a very high angle, such that the incidence is really high, you actually see the lakes look bright. This is in Minnesota, so there's lots of lakes around here. They all look bright in this image. It's the same thing we see here. Pungamare here looks brighter than its surroundings for the same reason. You're seeing essentially a reflection of the sky in the lake itself. But if you're just looking at that, you'd expect it to all look the same, right? It would all be the uniform brightness. You look back at these lakes in Minnesota, right? They're all about the same brightness across the lake. You don't see the giant spots on the middle of the lake. And so we're seeing these giant spots on the middle of Pungamare. What's going on? Well, let's see. Whoops. Preview. All right, what are you seeing? Well, here's maybe an example of another picture taking out the side of an airplane. Here's a specular reflection off the Great Salt Lake in Utah. And if you look right next to that specular reflection, you see this other bright stuff out in the middle of the lake. Similarly, you look up here, you see this bright stuff in the middle of the lake. That is specular reflections off the lake too, but not off a flat lake, but rather off a wavy lake. So wavy lakes spread out the glare, the glint off of the sun, so you can see that on a wide, it essentially spreads the brightness out over a wider surface. And so that's what I think we're seeing here in this image. We're seeing some isolated areas here where we're seeing a rough liquid surface instead of a solid liquid surface. Well, what does a rough liquid surface mean? Presumably this means wave activity on the surface of Titan. So what I was able to do was sort of fit this to figure out what the typical angle of the waves are, okay? And so if you calculate that out, you figure out that based on the overall brightness of these little pink spots, the waves on Titan must be about 6 degrees, so maybe about this high. I was like, wait, 6 degrees, that seems pretty high, right? I mean, you get some sort of couple meter long wave that's 6 degrees, that could be pretty big. I was like, this is pretty cool. So some colleagues of mine did some calculations for in Titan's gravity, which is only 1/7 the gravity on Earth, and in Titan's the viscosity expected of a liquid methane sea, and if you use the density of Titan's air, and you look at how fast the winds would have to go to create this 6-degree slope, the answer is only about 0.75 meters per second. So winds blowing about this fast. So not very fast, but then again, in the low gravity and high air density on Titan, this is enough, we think, to incite wave activity. So you can calculate in a computer model, all right, if you have waves that are blowing at 0.75 meters per second, how big are the waves? I was like, all right, these are going to be great. It turns out, all right, so here's that 0.75 value. You follow it over, and you find that the waves that we discovered on Titan are about this big. Okay, so we all recommend that you put off your surfing vacations to Titan until later, when the winds should pick up. We do think that as we go into further close to summer, to northern summer, the winds should pick up, and therefore the height of the waves will increase. So this is, if you're a southern or a Northern California Santa Cruz surfer, this is not your time of year on Titan. But what's exciting about this is these are the first time we've discovered, sea surface waves outside the Earth. Not a huge surprise, since Titans are the first seas we found outside the Earth, right? That we'd find it in the same place. But what it means, first of all, is that I was worried. You see these giant expanses of liquid. Well, you don't really know what they are. You don't know what they're composed of. You don't know what they have suspended in them. Molasses, or something with high viscosity, could easily have formed the same thing. But in order for us to have waves inside it at all by winds, you really need to have a relatively low viscosity fluid. So what this confirms is that we're looking at something that's really is akin to the lakes and seas and oceans of Earth, in that it's relatively low viscosity. You could splash around in it. Furthermore, if we send a probe down into it, it will actually splash down and not splat into a molasses-like surface, which would be a good thing if we ever get the money for such a mission. This is a more recent image. This is the way we name our images is via what flyby there were. So this is the 104th close flyby of Titan that Cassini made, and it was only last fall. And this is a pretty cool image because I think it shows a lot of what we're looking at. If you look at it here, this is one of those giant specular reflections. So imagine you have your sunglasses on. But I didn't. If I'd actually shown this specular reflection at its appropriate brightness, you wouldn't be able to see anything else at all, because it would be so much brighter than everything else you're looking at. So this is one of those giant specular reflections. The north pole of Titan is about right there. And we're looking at some of these north polar seas from the other side, from that other image I showed at the beginning. This is Kraken Mare, the largest sea. This is Punga Mare, where we saw those waves, the 2-centimeter waves. This right here is actually a cloud. So we're starting to see cloud activity pick up near the north pole of Titan. And this is exciting because this represents rain ultimately, right? These are thunderstorm clouds, except on Earth you'd call them thunderstorm clouds. But we don't think there's actually thunder or lightning on Titan. We've actually looked. We've listened for it. You don't have any lightning here in Northern California. So if you've ever been on a vacation to Florida or the Midwest or somewhere they have thunderstorms, you'd remember that if you're listening to your old FM radio during a thunderstorm, you can hear as static on the radio when there's lightning around you. So we've listened for lightning, and we've looked for lightning in the optical. We haven't seen any. So these are thunderstorms without the thunder and stuff. But it's the same sort of convective storm activity that we think is driven ultimately by methane condensation. These are methane clouds in the atmosphere, and are providing methane rain to the surface and perhaps replenishing the liquid in the lakes and seas we have on the surface there. So I was kind of surprised when I first found this. I thought, well, if you think about a lake or a sea on the Earth, you expect that, how would you get waves on one part and no waves on another part, or different waves on another part? Shouldn't it all be the same? Well, that's the way astronomers think. People that look at the Earth know better. So this image on the right is an image of Earth from a weather satellite of the Mediterranean Sea. And this is the Sahara down here, and this is Greece, and this is the island of Crete in the Mediterranean Sea. And the specular point here is about right here. And what you can see is that the Mediterranean is way complicated. Instead of everything having about the same waves, you see some areas that have inhibited wave activity. So maybe there was an oil spill or something here, or maybe there's less wind inciting wave activity. In other places, you get enhanced wave activity. In fact, it seems to be driven by this is enhanced by winds coming off of the island itself here, or ocean currents that may be driving these differences. So this was sort of a revelation to me to realize that it's actually normal for a lake or a sea not to all look the same, for different parts of it to have very different activity going on. In fact, this is that same T104 image from last fall, and I've zoomed in on part of it, this part right here. And you can see more of this bright pink stuff, orange stuff, it looks orange here, that corresponds to what we think is more wave activity. So this is really exciting. We saw no waves from 2006 until 2013. And now we're starting to see many more waves all over the place. And in fact, we've seen them in multiple places and for multiple reasons. So this could mean that we're seeing sort of a pickup of storm and wave activity near and around Titan seas as we proceed into the north polar summer, which is very exciting. So if we're trying to look about life in the seas, we need to have something dissolved in it. We still think carbon is a good choice for our building blocks for life. This is the second requirement. And so if you're looking for carbon dissolved in the seas, actually we think carbon might dissolve okay in liquid methane because liquid methane is a nonpolar solvent and should be able to dissolve other nonpolar carbon molecules. So do we see that? Well, we think we may have. This is a radar image of a particular area south of Ligeia Mare, and you can see several nice lakes here. This one's called Venernlocus. And when I look at it with my instrument in the infrared, they look like this. We still see the dark seas, but some of these dark seas have bathtub rings around them. So who's driven to Vegas lately and seen Lake Mead and the edges of it? Anybody? No one goes to Vegas? All right, you've been to Vegas. All right, come on. I guess what happens in Vegas stays in Vegas, so no one's telling me what's going on. Okay, if you go there, the extreme drought that you and the rest of the western U.S. have been going through has actually led to the lake levels at that lake to go dramatically down. And if you look around the outside, there's this white rim all around Lake Mead, and that's caused because you had dissolved materials in the lake that once it evaporated, those dissolved materials could no longer stay in solution, and they precipitated out as a fine-grained, sort of salty salty surface, solid surface around the lake. The same thing may be happening on Titan, and this may be our evidence for it. We see these sort of bathtub rings around several different lakes, and we also see these lakes here that look like they look like holes with no lakes in them, but when you look at them in the infrared, they stick out as having these same deposits of evaporite on them. This is the same stuff if you never wash your tub, okay? It's the same stuff that builds up on there if you have hard water. That hard water is because of a lot of dissolved materials. So what we may be seeing here, what we think we're seeing, is observational evidence that you are dissolving materials, probably carbon-bearing materials, inside Titan's lakes. And this is particularly relevant to the idea of, can life proceed there? Or can you get biological-like chemistry in these seas? You can't do it if you just have pure methane, okay? There's nothing there to form the life out of. You need some sort of higher order hydrocarbons dissolved in that lake in order to make the whole thing work. And what we've seen, is evidence that this stuff does exist. It does dissolve in the Titan environment. And so these lakes and seas probably do have at least some amount of hydrocarbon that could potentially lead to biological or maybe pre-biological processes. So this is just a zoom in on some of those lakes. Some of them are showing this evaporite stuff. This is what the stuff that's left over that was in solution that precipitates out. This solid stuff that's the white stuff at the end, at the outside of Lake Mead is called evaporite. And on Earth, what's the most common evaporite? Who's been to the bottom of Death Valley? Salt, right? You take a bunch of ocean water, you let it evaporate, you're left with salt. Well, salt is NaCl. It dissolves well in water. It dissolves like crap in liquid methane, okay? So this is not salt that we're looking at. What dissolves well in liquid methane is organic material. So we think that if you have if anything, this stuff outside is probably organics ultimately derived from the atmospheric methane via chemical processes. And this is a terrestrial analog. About 15,000 years ago, during the last glaciation, it was colder and wetter here in the western U.S. And in fact, the Great Salt Lake occupied a much larger area. And it was still salty, such that when that Great Salt Lake dried up, it left this giant salt flat out west of the Great Salt Lake that if you're driving on Interstate 80 here to Salt Lake from here, you'll recognize this because it's like an hour and a half of your journey, okay? It's like this is a huge salt flat. And this is what we think we may be seeing the analog of on Titan. If you think about a salt flat on Earth, you wouldn't think about this being evidence for life. But because it's organics that dissolve in Titan seas, we think it may be more of an indicator for life on Titan. So you want to look at what molecules should be on those lakes, what should dissolve in those lakes, what do we expect to see. These are two different calculations, both made in the same year, of what those lakes should have in them, other than methane and ethane. These are the solids. What I take away from this is that these don't match. No part of this matches. Okay. It turns out doing experiments on liquid methane and what dissolves in liquid methane at very cold temperatures that you see on Titan at 90 Kelvin is hard. And in fact, if you try to extrapolate what should happen from experiments at higher temperatures down, you don't always get the right answer. And so this is part of what ongoing research by, in fact, people in this room, Mike Malaska at JPL, is studying how much stuff dissolves, what stuff dissolves, because it's a very important step to figure out what's going to be there as the ingredients life might be able to build things out of. I thought of doing these kind of experiments, but I'm not a chemist, right? If you take liquid methane in a lab, that's really kind of like a pipe bomb, right? So I decided to leave it to the professionals and not get too excited. So this is a result from Mike Malaska's paper from last year, looking at various different carbon compounds and how they dissolve in liquid methane experimentally. And he did this with a couple of different molecules. Here's benzene, here's more complicated molecules. And this leads to what I think is the biggest problem and why there may not be life in Titan seas, because as you get to larger and larger molecules, they dissolve worse. It becomes harder to get them to dissolve in the liquid. Okay? And this is a problem because if you look at something like DNA, it's huge. It's a gigantic molecule that's way bigger than even these guys. Yet these guys are starting to dissolve only at a very small level inside the liquid material. So what this ultimately means, I think, and what worries me, is that this may mean that dissolving higher order hydrocarbons may be so difficult at Titan's temperatures that it may be hard to actually get what we need for life to occur. But like we did on Earth, where we assumed you need sunlight, I think the test, this does not strike me as something that we should try to determine theoretically. This is really something we need to determine experimentally, that we need to observe. When we look at the composition of the particles in Titan's atmosphere, the haze particles in Titan's atmosphere from Cassini, we see that there's tons of carbon around. In fact, there's a lot of very complicated carbon materials. So this is how much of each compound there is as a function of how big or how massive the molecule is. So this is sort of one carbon and a bunch of hydrogens on it. This is 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. So this is maybe benzene, C6H6 can get up here. So there's plenty of this stuff around, actually, in Titan's atmosphere. This place is an organic chemistry wonderland, presumably with no life in the outer atmosphere. But this can all provide the energy that you might need at Titan as well. All these molecules are excited ultimately by ultraviolet from the sun, breaks apart the methane and builds it into higher order hydrocarbons. And these tend to be pretty nasty and could be used potentially by life to be able to generate energy in the seas themselves. The reason what we really care about, though, are how much are there molecules that are heavier than this, the ones that might be biological, which would be way over here on the chart. Okay? Turns out, when we sent Cassini, launched in 1997, we had no idea there was going to be anything this awesome at Titan. In fact, this is where the instrument cuts off. It doesn't go any higher than that. Okay? So there's a lot of prospects for exploring the chemistry of Titan seas better. And in fact, this has been proposed. This was a proposed mission to land a capsule that would float on the seas of Titan. And this capsule was going to be called Time, the Titan Mare Explorer. Mare means sea in Latin. So this thing was going to splash down, and it had a mass spectrometer that could be able to suck in some of the seawater and determine exactly what it is dissolved in there. And the idea is this is a potential search for, if not life, pre-biological chemistry that might lead to life, that might be able to constrain where and when life can form and evolve. So this is important because if you look back at life on Earth, when did life start? Well, we don't know. The earliest evidence we have is maybe from 3.5 billion years ago. So we don't know what happened in the extra billion years before that. In order to figure that out, one way to do that is to look other places and find where else and how else life might be able to form, or even where it can't form. Maybe Titan is an end member in the other direction. Maybe this is a place where we know life hasn't formed and evolved. And that's also a very important data point, trying to determine what the ultimate scope of life may be, not just in our solar system, but in the universe in general, as we find planets around other stars to a higher degree. So I'm just going to leave these conclusions up. I'd rather take your questions than say what I just said again. So thanks.
Thanks. The floor is open for questions. I'm going to start with you.
Life also needs a container. Is there anything analogous to lipids in the seas?
Okay, well, so there's this brand new paper that just came out on Friday that I'm afraid I have not had a chance to read in detail. But there's a new paper out in Science, it's called Science Advances, about how you could build a membrane out of what we may be able to find and what may be able to dissolve in Titan seas. So that question is being asked, and you look that paper up and you'll be able to find the answer. I wish I could tell you, but I haven't read it yet, so I can't give you a cogent answer on that.
If you had a chance to define one key measurement from your perspective, what would that be going forward?
I think really the thing to be measured is if we can measure the actual composition of what's dissolved in those seas. So I think it's this mass spectrometer that you need. You actually need to get down in the seas. This is not something we can do from a remote measurement, unfortunately. We've sort of tried with Cassini, and there's not, you can't see a spectrum tight enough to be able to get the detail you need. So you really need to be down in the seas themselves. What we're looking for is, do you see the kind of distribution of materials and distribution of molecules that you might see in a life form where it's basically highly out of equilibrium. Right? If you look at a life form, or if you look at just an abiotic process, it's going to produce various different, say, amino acids in proportion to how hard it is to make those kinetically. And so if you see something that just follows the kinetic reaction rates, that's probably abiotic. If you see something that's strongly different from that, then that's interesting, and that's weird, and that's the kind of marker that we're looking for to determine if there may be a process going on here that's not just normal organic chemistry. Yeah?
Yes, I enjoyed your talk, very interesting. But let me take the liberty to address you a question.
Yeah.
Something is missing. A clear-cut definition for life.
The NASA definition for life is a chemical system undergoing evolution. That's what life is.
Oh, okay. That's fine. Thanks. Yeah, and what is evolution?
You'll have to read the Darwin's Origin of Species.
What?
You'll have to read Origin of Species. So evolution is you have to have some mechanism to be able to store information, and some way for that information to mutate over time, and then some sort of selective process to select the ones that work.
I think some additional work on this resolution definition should be desired.
Many people have tried to do this, and in fact, you look at the biologist's definition of life, it'll go for half a page. So that's why I like the NASA definition. It's concise, and I think it may be difficult to measure, but I think it's both concise and precise in that you really be able to know what you're looking at if you do the right measurements to find it. Yeah, Matja.
Jason, can you put the Huygens landing site in context of our understanding of how Titan operates in 2015?
Sure. So we actually have already landed a lander on Titan. It landed in 2005, but it landed near the equator. Do I have a good map of where that might have been? It turns out when Huygens was designed in the 1990s, we didn't know what it was going to hit, and there were predictions that it might land in liquid. And so it was actually designed to float. It was designed to do speed of sound measurements in the liquid it would hit. But it turns out it didn't land on liquid. It didn't land here, but it landed on a site that looks kind of like this. It landed on a plane, an outwash plane of one of these channels near some of these icy mountains. So it happens, and in fact, it saw some of these sand dunes in the distance. So it actually landed in sort of Titan's Sahara. So even then, it was able to see some liquid methane exhaled from the surface as it hit. So even that Sahara-like surface is somewhat moist. So if you get down beneath the surface, there's some soil moisture. If you were to dig down, it wouldn't be totally dry underneath. But as it turns out, this is the danger, of course, in sending a single giant mission, is that you can't learn about the target before you get there. And so we're able to land, but it was in a very different environment near the equator and not up near the poles, where we now would land if we were trying to land in the liquid.
I have a crazy comment.
Yeah, go for it.
We know that on our planet, that if you observe the upper atmosphere, you will see that there is in fact life over there. So instead of landing on a lake, instead of digging or whatever, why don't we just try to observe the top of the troposphere of Titan and see if there is a signature of life?
Yeah, that's a good point. There have been bacteria cultured from the outer atmosphere of the Earth. And of course, there was some horrible press release saying, oh, therefore it must come from aliens, because it couldn't possibly come from the surface of the Earth. Do you remember this? Anyway, it was horribly embarrassing, the entire field. The difficulties in that is Titan's atmosphere is actually much fatter than Earth's. That has to do with its low gravity. So if you go up about 100 kilometers, you're essentially up out of the atmosphere. And if you flew 100 kilometers, we'd consider you an astronaut. In Titan, you'd still be well in the atmosphere. You have to get up to 1,000 kilometers to be out of the atmosphere. So it's a little harder. There's less vigorous convection on the surface because there's less sunlight. But it's not a crazy idea to be able to look at it in the outer atmosphere as well, though I think the bigger difficulty is that the chemistry in the outer atmosphere is really dominated by abiological processes. It's dominated by solar ultraviolet input and by actually energetic ions coming in from Saturn's magnetosphere. So it may be, although that might work, I think it's kind of going to be difficult to tease out any biological from abiological signal. Yes?
I've got a comment and a question. The comment is that I don't believe during the entire talk you mentioned temperature.
Sure.
Pretty low.
I maybe referred to it, but I didn't give you a number. So because you're 10 times further from the sun, the temperature is about a third the temperature on the Earth. So it's about 90 degrees Kelvin.
90 Kelvin.
90 Kelvin. So like liquid nitrogen is 77 Kelvin.
Yeah, methane, the liquid methane is what?
Right. The triple point of methane, it depends on how much dissolved nitrogen there is. It's about that number. It's about 88, 89, depending on what it's in it and whether you have condensation.
So just a comment, and that is that certainly the chemistry of life as we know it, obviously, is different. But any of the reactions that are engaged in our life at those temperatures would have characteristic times, well beyond the lifetime
millions of years.
The solar. Well, no, more than that.
Yeah, potentially. Okay, so this is a very good question. The question of temperature. Oh, I'll let you finish, and then I'll go.
Well, let me.
It looks like you were going to keep going. Go ahead.
Complete the thought. So, my thought is that the numbers of or the chemistry that you have available to you to consider life under those conditions is very, very limited. The reactions might be limited just to photochemistry, and the number of structures possible are the organic structures possible, I would suggest is pretty small, and the complexity that life is. I mean, you did a nice job. You're a very energetic, entertaining speaker, but the question of life is a broad one, and it requires broad thinking in terms of complexity and certainly reaction rates and some thermodynamics. So
I don't disagree with you. If I were to place bet today as whether we're going to find life on Titan, I'm going to bet no, depending on what odds they give me. Okay, there are odds they give me at which I would make the bet, but at 1 to 1, I would bet no. As far as temperature goes, by your argument, you wouldn't expect to find, for instance, any life at the bottom of the ocean in the deep sea vents because it's too hot. The temperature there is 120 Celsius. Okay. However, evolution has designed its molecules specifically to operate in that temperature. So I think you're right. It's not obvious that it would work, but it's not also obvious to me that evolution might not be able to find a way to develop molecules that have enough appendages to be able to maintain their activity even at these temperatures. Though I agree with you. It's not obvious that this is going to be possible. Yeah.
So one of the bullet items on your last slide, could you tell us about the JET mission?
Oh, I didn't even get to that. Thank you. There are additional missions that we're thinking of flying in addition to this lake lander. One of them is maybe to be able to fly just an orbiter, a Saturn orbiter, but one with a better mass spectrometer that can measure up to much higher order hydrocarbons and measure it more precisely, and to be able to take imaging pictures of the surface. And this would be a cheaper mission. And this is one of the things that have been proposed to go forward. We haven't gotten any funding to go on that route yet. But the idea here is you'd fly through the Enceladus plume where it's spewing icy and water-laden materials out into space, fly through them with a mass spectrometer, and also fly through the outer atmosphere of Titan with our mass spectrometer, and then take pictures with the camera to characterize the lakes and what's going on around the lakes. It's sort of a precursor to what we might ultimately be able to do with the lake lander. I think what's exciting about Titan is there's all sorts of ways you can explore it. In fact, I proposed to send a nuclear-powered airplane, which is a little crazy, but it turns out with just the normal kind of radioisotope thermal generator, or a little more advanced version that's on Cassini or on the Voyagers, you generate enough power that in Titan's low gravity, high air density conditions, you can fly indefinitely. Essentially, you'd be limited by when NASA would stop funding you, funding would probably be the limiting reagent. And in doing so, you'd be able to take pictures of all over the surface. It would be really exciting. And Titan's fun because it's all these different solutions work. I don't know how many of you have seen recently, there's a YouTube video by Dr. Ralph Lorenz who explored using a submarine on Titan, which would also work and be able to discover all sorts of crazy things. So it's exciting because all sort of the vehicle types we think of on Earth, they all work on Titan. So you just got to think of which one you want to send next. Yeah.
Yeah, you sort of mentioned really quick about a large, vast area across there that's sand. You call it sand, and if it's really sand in the way we know of it, where does it come from? Because it takes a lot of energy to break stuff down into sand-like particles.
Sure, great question. I have a whole other talk on sand, but probably don't have time for that today. So I'll give you the brief version. This stuff, we call it sand because you calculate what kind of size particle would actually jump around on Titan, similar to the ones that form on Earth. It's the ones that are about the same size in radius, about 300 microns. And geologists, of which I'm not really one, but geologists define sand as something between 0.0625 and 2 millimeters in diameter. So it's a particle size range, not a composition. Okay, so this is not SiO2 sand like you'd see on a beautiful beach. If you head west to Half Moon Bay or something, you're not going to find the sand we see here. But at the same time, there's lots of different kinds of sand on Earth. Actually, if you go to Hawaii, there's black sand beaches made of basalt, or there's green sand beaches made of olivine. And so similarly, this is a sand that we think is made of organic material. So this is solid organic material. We don't know what produces the sand, but it's ultimately derived from this haze that's ubiquitous throughout Titan's atmosphere. So somehow that stuff all gathers together, and we've seen these giant 100-meter high, hundreds of kilometer long, longitudinal sand dunes that match in their size and scope the ones in Africa, say Namibia, Southwest Africa, or in the Sahara, very closely. In fact, next month I'm going to go to the United Arab Emirates, which also has a great set of these dunes and is politically stable enough that I hope I'm not going to get kidnapped there. So, but there must be some amount of wind to be able to produce these things. That's right. We don't know what those winds are and how strong they are. It would be great to have sort of like a meteorology lander down on the surface of Titan. But they must be about the same level. Actually, about 1 meter per second is the calculation for how fast the winds would have to go in order to entrain material and produce the sand dunes. So Titan is definitely a very energetic environment, and there are enough winds to be able to have these same kind of activities, the same physical processes that we see on Earth. Yeah?
Hi. What are the spectroscopic features that distinguish evaporates from the other bedrocks?
Okay, so the question is, what spectroscopic signatures determine the evaporite? Well, the evaporite is white. Everything else on Titan has some amount of water ice in it. And in fact, what the most distinguishing feature of the evaporite is that its signature has no evidence of water ice or water in it at all. So it's completely non-water stuff. We've been looking for different absorptions of different specific molecules on Titan. And so far, we found that one due to ethane in the lakes. There's only one other one we've seen, and it happens to be an absorption at 4.92 microns that we haven't been able to identify. But Titan is made of all these crazy organics, and they're all mixed together. Something has been producing in the evaporites. In order to be able to have a single absorption line like that, there must be some sort of mechanism that is, percolating and being able to purify that stuff, and being able to do, the stuff that dissolves and then precipitates would be one way to do that. And so there is this one, absorption line that we haven't been able to identify. If you have any ideas, what absorbs at 4.92 microns? Let me know, because we're trying to figure it out. Yes?
Jonathan Lunine has been saying that Titan is the place for astrobiology, because if we go to places like Mars or Enceladus or Europa, we might find life that's just a cousin. If we really want to understand life, we need to go where it's life as we don't know it. And so he would say, skip Mars, skip Enceladus, skip Europa, and concentrate on Titan. Would you go that far?
Oh, that sounds great. I would love that. No, Titan's obviously the place. And because it's more, not only is it a good spot for life, but there's also a very interesting atmosphere. There's also very interesting geology. There's interesting interactions with the magnetosphere. Titan is actually really a very diverse and interesting object from a planetary science perspective, in addition from a life perspective, right? Yeah, if you detect life on Europa and it happens to have the same 22 amino acids that we do, yeah, it's probably, panspermia or something, right? It's probably not an actual separate genesis of life. Whereas this very difficult to imagine how true, Earth life, if you got an Earth rock off of Earth somehow by an impact and tossed it out to the outer solar system, could have possibly seeded life in a different solvent. I think it would be much more challenging. So yeah, you should next time you talk to the the NASA brass, let them know your particular bias, assuming it's the same as Jonathan O'Neill's. Otherwise, don't tell him. Yes.
Yes, I wanted actually to respond to the gentleman's question in the back.
Yeah, go for it.
The differences.
You know more than me, so yeah.
So you're right. You know, at Titan's really low temperatures, making and breaking covalent bonds is going to be really, really difficult. And even at the low temperatures, things that we have on Earth that are very transient in our system, like those hydrogen bonds, on Titan, those are almost going to be as hard as the covalent bonds are here on Earth. So when you start thinking about going and looking at chemistries and interactions on Titan, you're actually going to have to scale down a bit. A lot of the things on Earth that are just made and broken, you know, transiently, little, you know, aromatic pi interactions and things like that, those might be the things and structures that are being used or could be used by Titan organisms or prebiotic processes. So it's not only just a different like chemistry and different chemical structures, it could be actually different interactions at the molecular level of what potentially could be occurring on Titan.
This is what I think is so exciting, is that, you know, things on Titan are so different that we really haven't even started to think about what those differences, you know, the implications of those differences. We're just starting to get going with that.
Okay, Jason. Thank you very much for this talk. Thanks a lot. So as a token of our appreciation for being here at the SETI Institute, you get this amazing cup to carry with you. And
thank you.
Please fill it up with methane and study the type of life you can have on it.
Thanks. Thanks everybody for coming.